to troubleshoot the UPS power quality issues, begin by thoroughly investigating the electrical grounding system. Ensure that the UPS, all connected equipment, and the electrical outlets are properly grounded. Carefully inspect for any loose or corroded grounding connections and correct them as needed. Next, determine if the neutral and ground terminals are bonded together, either within the UPS itself or at the service entrance. If these terminals are not properly bonded, it could lead to voltage on the neutral conductor and create a risk of electrical shock. Measure the current draw on each phase of the UPS to assess for any load imbalances. Excessive load imbalances can place undue strain on the UPS, potentially leading to premature failures. Employ a power quality analyzer to measure the level of harmonic distortion present in the incoming power line. Elevated levels of harmonics can disrupt the normal operation of the UPS and cause overheating. Identify any equipment that may draw high inrush currents when starting up. Make certain that the UPS has sufficient capacity to effectively handle these inrush currents. Verify that surge suppression devices are installed and are functioning correctly. Surges can cause damage to the UPS or any connected equipment, which could result in power quality problems. Check the temperature and humidity levels in the environment where the UPS is installed. Extreme temperatures or high humidity can negatively impact the UPS performance. Determine the age of the UPS and review its maintenance history. Older UPS units or those that have not been properly maintained are more likely to experience failures. Utilize a line noise analyzer to measure for the presence of transients or spikes in the incoming power line. Excessive line noise can interfere with the operation of the UPS. Check to see if power factor correction devices are installed and are functioning properly. Low power factor can reduce the efficiency of the UPS and increase the load on it. To elaborate on each of these points, firstly, consider the importance of proper grounding. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly clear the faults. Without a good ground, fault currents can flow through unintended paths such as equipment cases or people, creating a shock hazard. The grounding system should be checked for continuity and resistance using a ground resistance tester. The resistance to ground should be as low as possible, ideally less than 5 ohms as recommended by IEEE Standard 142. Secondly, the neutral to ground bond is crucial for establishing a reference point for voltage. In a properly functioning system, the neutral is bonded to ground at the service entrance, creating a single point where the neutral and ground are at the same potential. This bond ensures that the voltage between neutral and ground is close to zero. If this bond is missing or compromised, the neutral can float to a different voltage, creating a shock hazard and causing equipment malfunction. It is important to verify the location and integrity of the neutral to ground bond. Thirdly, load imbalance can cause several problems for a UPS. A UPS is designed to provide a balanced output voltage to all phases. If the load is significantly imbalanced, the UPS may have difficulty maintaining a stable output voltage, leading to voltage fluctuations or even UPS shutdown. Furthermore, load imbalance can cause excessive current flow in one or more phases of the UPS, leading to overheating and premature failure. To check for load imbalance, measure the current on each phase using an ammeter or a clamp-on ammeter. The current on each phase should be within 20% of the average current. If the imbalance is greater than 20%, redistribute the load to balance the current on each phase. Fourthly, harmonic distortion is a measure of the distortion of the voltage or current waveform from its ideal sinusoidal shape. Harmonics are caused by nonlinear loads, such as electronic devices, which draw current impulses rather than in a smooth sinusoidal waveform. High levels of harmonics can cause a variety of problems, including overheating of transformers and conductors, malfunction of electronic equipment, and increased energy consumption. To measure harmonic distortion, use a power quality analyzer. The total harmonic distortion, or THD, should be less than 5%, as recommended by IEEE Standard 519. If the THD is greater than 5%, consider installing harmonic filters to reduce the level of harmonics. Fifthly, inrush current is the high current that flows when equipment is first turned on. This current can be several times the normal operating current of the equipment. If the UPS is not sized to handle the inrush current, it may trip or shut down. To identify equipment that may draw high inrush currents, check the equipment nameplate for the inrush current rating or use an inrush current meter to measure the inrush current. Ensure that the UPS has adequate capacity to handle these inrush currents. Sixthly, surge protection devices, or SPDs, protect equipment from voltage surges, which are sudden increases in voltage that can damage or destroy electronic equipment. Surges can be caused by lightning strikes, switching of electrical loads, or other events. SPD work by diverting the surge current to ground, protecting the equipment connected to the circuit. Verify that SPD are installed at the service entrance and at any critical equipment. Check the SPD regularly to ensure that they are functioning properly. Seventhly, environmental factors such as temperature and humidity can affect the performance and reliability of a UPS. High temperatures can cause the UPS to overheat, reducing its efficiency and lifespan. High humidity can cause corrosion and condensation, which can damage electronic components. Ensure that the UPS is installed in a well-ventilated area and that the temperature and humidity are within the manufacturer's recommended limits. Eighthly, the age and maintenance history of a UPS can affect its reliability. Older UPS units are more likely to fail than newer units. Regular maintenance, such as battery replacement and cleaning, can help to extend the life of the UPS and prevent failures. Determine the age of the UPS and review its maintenance history. If the UPS is more than 5 years old, consider replacing the batteries. Ninthly, line noise refers to unwanted electrical signals that can interfere with the operation of electronic equipment. Line noise can be caused by a variety of sources, including electromagnetic interference, radio frequency interference, and switching transients. Excessive line noise can cause equipment malfunction, data corruption, and other problems. Use a line noise analyzer to measure the presence of transients or spikes on the incoming power line. If excessive line noise is present, consider installing line filters to reduce the level of noise. Tenthly, power factor is a measure of how efficient the electrical power is being used. A power factor of 1 indicates that all of the power being supplied is being used to do work. A power factor of less than 1 indicates that some of the power is being wasted. Poor power factor can reduce the efficiency of the UPS and increase its load. Check if power factor correction devices are installed and functioning properly. If the power factor is low, consider installing power factor correction capacitors to improve the power factor. By thoroughly investigating these potential system issues, it will be more efficient to diagnose the cause of the UPS problems and implement the appropriate corrective actions. Remember to consult with qualified electrical professionals for any work involving electrical systems. Safety should be a top priority when dealing with electrical equipment. Always de-energize the circuit before working on it and follow all applicable safety procedures. Now let's delve deeper into each of these points to provide a more comprehensive understanding. Expanding on electrical grounding, it's crucial to understand that a properly designed and maintained grounding system is not just about safety, it's also about ensuring the reliable operation of electronic equipment. A good ground provides a stable reference point for voltage, which is essential for sensitive electronic circuits. The grounding system should consist of a network of interconnected conductors that provide a low impedance path to ground. This network should include a grounding electrode system, such as ground rods or a buried ground ring, and a grounding conductor that connects the equipment to the grounding electrode system. The grounding conductor should be sized appropriately for the equipment it is serving, in accordance with the National Electrical Code, NEC. It is also important to ensure that all grounding connections are clean and tight. Loose or corroded connections can increase the resistance of the grounding path, which can reduce its effectiveness. Regular inspection and maintenance of the grounding system are essential to ensure that it continues to provide adequate protection. When checking the neutral to ground bond, it is important to understand the difference between a separately derived system and a non-separately derived system. A separately derived system, such as a generator or a UPS, has its own neutral to ground bond. A non-separately derived system, such as a utility service, has its neutral to ground bond at the service entrance. In a separately derived system, the neutral to ground bond should be located at the source of the power. In a non-separately derived system, the neutral to ground bond should be located at the service entrance. It is important to avoid creating multiple neutral to ground bonds in the same system, as this can create circulating currents that can cause equipment malfunction and increase the risk of electrical shock. When measuring load imbalance, it is important to use a true RMS ammeter. A true RMS ammeter will accurately measure the current even if the waveform is distorted. The current on each phase should be measured under normal operating conditions. If the load is constantly changing, it may be necessary to take multiple measurements over a period of time. If the load imbalance is significant, it may be necessary to redistribute the load to balance the current on each phase. This can be done by moving equipment from one phase to another or by installing additional circuits. When analyzing harmonic distortion, it is important to understand the different types of harmonics. Harmonics are multiples of the fundamental frequency, which is typically 60 Hz in the United States. The most common harmonics are the odd harmonics, such as the third, fifth, and seventh harmonics. Even harmonics are less common, but can still cause problems. The level of harmonic distortion is typically measured as total harmonic distortion, THD, which is the ratio of the RMS value of the harmonic components to the RMS value of the fundamental component. A high level of harmonic distortion can cause a variety of problems, including overheating of transformers and conductors, malfunction of electronic equipment, and increased energy consumption. Harmonic filters can be used to reduce the level of harmonics. These filters typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. When dealing with inrush currents, it is important to select a UPS that is sized appropriately for the load. The UPS should have a surge current rating that is high enough to handle the inrush current of the equipment being powered. It may also be necessary to use soft start devices to reduce the inrush current of some equipment. Soft start devices gradually increase the voltage applied to the equipment, which reduces the inrush current. When verifying surge protection, it is important to ensure that the SPD are properly installed and grounded. The SPD should be installed as close as possible to the equipment being protected. The grounding conductor for the SPD should be short and direct. It is also important to check the SPD regularly to ensure that they are functioning properly. SPD have a limited lifespan and will eventually need to be replaced. When considering environmental factors, it is important to maintain the temperature and humidity within the manufacturer's recommended limits. High temperatures can cause the UPS to overheat, which can reduce its lifespan. High humidity can cause corrosion and condensation, which can damage electronic components. The UPS should be installed in a well-ventilated area. If the temperature or humidity is too high, it may be necessary to install additional cooling or dehumidification equipment. When evaluating the age and maintenance of the UPS, it is important to keep accurate records of all maintenance activities. This will help to identify any potential problems early on. The batteries in the UPS should be replaced regularly, typically every 3 to 5 years. The UPS should also be cleaned regularly to remove dust and debris. When measuring line noise, it is important to use a line noise analyzer that is capable of measuring both common mode noise and differential mode noise. Common mode noise is noise that is present on both the hot and neutral conductors with respect to ground. Differential mode noise is noise that is present between the hot and neutral conductors. Line filters can be used to reduce the level of line noise. These filters typically consist of inductors and capacitors that are designed to block high-frequency noise. When addressing power factor correction, it is important to understand the difference between lagging power factor and leading power factor. Lagging power factor is caused by inductive loads such as motors and transformers. Leading power factor is caused by capacitive loads such as capacitors and electronic equipment. Power factor correction capacitors can be used to improve the power factor. These capacitors are typically installed in parallel with the inductive loads. Remember that electrical work can be dangerous. Always follow all applicable safety procedures and consult with a qualified electrical professional if you have any questions or concerns. By carefully considering these factors, you can effectively troubleshoot UPS power quality issues and ensure the reliable operation of your equipment. It's essential to approach the investigation systematically and methodically, documenting all findings and actions taken. This thorough approach will not only help resolve the current issues but also prevent future problems. Remember that continuous monitoring and preventative maintenance are key to maintaining a healthy and reliable power system.